Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 24 of Algebraic Topology. As you remember, in our previous lecture we discussed what is deformation retract, and then we discussed some further facts about reduced homology, and then we discussed two major tools for calculating singular homology, XCN and MV theorem. And then we went on to apply these things, and we calculated the homology and why homology is useful. Okay. In today's lecture we are going to continue our discussion about the understanding of homology, and of course this understanding will help us in calculating homology. So in particular we are going to discuss the relation of homology and the fundamental group. Okay, so in today's lecture we will first discuss what is free product of groups. So in our first lecture we discussed some basic properties of groups, and we didn't discuss about the free products of group, although we discussed about the free groups. But in today's lecture we will see what is free product of groups, and then this is needed in our next theorem, which is Van Kampen's theorem, and in this theorem we will see how to calculate fundamental group of complicated topological spaces. Okay, and then we will go on and try to see the relationship between the first homology and pi 1, and then in the last we will just have a very brief overview of the relation between simplification and singular homology. Okay, so let's have an overview of the free groups. So what is a free group? So consider a set of alphabets, this A, and we call a symbol of the form a I raised to power n, where n is any integer, a syllable, and an array of syllables written in juxtaposition. So just write down the syllables in this form. For example, this is called a word in the alphabets of the set capital A. So for example, if our capital A set is ABC, then A square is a syllable, B cube is a syllable, C raised to power 1 is a syllable. So we if we just write these three syllables in juxtaposition, then this is going to be a word. Similarly, A raised to power 1 and B raised to power 10, these are two syllables, and written in juxtaposition, written with each other like this. So this is a word. Similarly, we can write down other words as well. So for example, in this A is equal to ABC, we can write down another word, A raised to power -2, B raised to power 3, and let's say C is equal to 5. Okay, so this is another word, and similarly we can write down other words, and if we apply these two rules for reducing the word, okay, then the remaining elements will form the group. Okay, so how we reduce the word? So if we have ai raised to power m, ai raised to power n, then we can add the powers like this, and m plus n is going to be another integer, and if there is power ai raised to power 0, then we replace it with the identity. Okay, so with these two reduction rules, okay, so the set of reduced words is denoted by f of a, and under the operation just described is basically the free group generated by a. Okay, so roughly speaking, what is a free group on a set A which is equal to AB? So we can say that this is a collection of all words, so a collection of all elements of the form. So ai raised to power n1, b raised to power m1, a raised to power n2, b raised to power m2, up to so on, a raised to power, let's say, nk, and b raised to power mk. Okay, so this is a general element of f of a, where A is basically set of two elements. So that's how the free a general element of the free group generated by this set A will look like. Okay, and whenever there is repetition of A and B, okay, so if there are two consecutive B's or two consecutive powers of A's, then we can use these reduction rules. Okay, so if after reducing the consecutive powers of B or consecutive powers of A, if we get 0, then we replace that 0 with identity. Okay, so using these two rules we can also define the inverse. So for example, if I have A raised to power n1 and B raised to power m1, then we can easily define the inverse of this. So using keeping in mind these two rules, we can define the inverse of this to be B raised to power minus m1, because these are the two consecutive powers of B, and when we will add them, then m1 minus m1 will be 0, and B raised to power 0 according to this second reduction rule will be identity, and similarly A raised to power minus n1. Okay, so this element is the inverse of this element. Okay, so this is just an overview of the free group generated by the set A. Now we also know that we can take direct sum of two groups. So for example, if I have integers, then I can take the direct sum of integers with itself, and so the generator of this Z can be denoted as 1 0, and the generator of this Z can be denoted by 0 1. Okay, so of course this is Z, it is generated by one element, and this is Z, this is infinite cyclic group generated by one element. So the point is this 1 0 and 0 1, they commute with each other, because we know that 1 0 plus 0 1 is equal to 0 1 plus 1 0. Okay, so they commute with each other. In other words, we can say that the generator of this set commute with the generator of this set. Okay, so we know that this Z is basically a free group. Okay, so the elements of Z can be written as, so elements of Z can be written as the powers of one element or one symbol. Okay, so for example, I can write down x, x square, x cube, x3, x4, up to so on, and of course 1 and the negative powers of x. Okay, so we can say that this is infinite cyclic group, or we can say that this is a free group on one element. Okay, so Z is basically equal to the free group generated by this A, where A is equal to only one alphabet x. So this Z is free and this Z is free, but when we take the direct sum, then we have one relation. Okay, so let's call this generator 1 0, and let's call it A, and let's call the generator of this Z, which is 0 1, as B. Now the point is this implies that A plus B is equal to B plus A. So there is one relation between the elements of this Z and this Z. So in other words, we can say that this Z plus Z is not really a free group, but this is free abelian group. Okay, so which is not really free, because we are getting one relation. So free group is a group which has no relations, but there is one relation, and the relation is A plus B minus B plus A equal to 0. So this is one relation. Okay, now we can say that this is not really a free product. Okay, so we started from this Z, which is a free group, we started from another Z, which is a free group. So when we took this addition, special addition, which is the direct sum, then after taking this direct sum, the resulting group is not a free group. Okay, so now what we want is, if I have a free group and another free group, and when I take the free product of two free groups, then the result should be a free group. Our next aim is basically to construct a group containing given collection of groups G alpha, such that the elements of different subgroups G alpha does not commute with each other. So in this case, once again, the generator of this Z and generator of this Z commute with each other. We don't want that, and that's what we are going to define next, which is called the free product. Okay, so let's see how to define the free product. So given a collection of groups, we can define the free product denoted by this. Okay, so of course, if I have two groups, then I will write down the free product as G1 star G2. Okay, so up to so on. If I have three groups, then I can write down like this, and if I have 4 and up to so on. Okay, so the free product consists of all words of arbitrary finite length. Okay, so this is important. It should be finite length, and this m should be greater than or equal to 0, such that the following conditions hold. So number one condition is each letter in this expression belongs to the group G alpha I, and adjacent letters belong to different groups G alpha. Okay, so any of the element in this expression belongs to some group G alpha I, and secondly, adjacent letters belongs to different groups G alpha. Okay, so of course, if I have an expression of the form G1, G2, G3, G4, such that G2 and G3 belongs to some fixed G1, for example, then since G2 and G3 belongs to G1, then this implies that G2, G3 is equal to some element, let's call it G prime, belonging to G1, because G1 is a group. So we can just replace this word as G1, G prime, G4. Okay, so we can replace this consecutive appearance of two elements of the same group by their product. Okay, so this assumption is very practical. So whenever there is repetition, replace that repetition with the product in the corresponding group. And similarly, each letter in this is not the identity of this. So whenever there is identity, okay, so for example, if there is identity like this, G1 alpha 1, for example, okay, so and H and some other element H2 up to so on, so where 1 alpha 1 belongs to G alpha 1, then we just delete this identity and we write it down as G H H2. Okay, so applying these two rules, we get the free product of two groups. Okay, so let's consider an example. So so before we discussed the direct sum of Z with itself, now we are going to discuss what will be the free product of Z with itself. Of course, we know that Z is generated by one element, it's infinite cyclic group. So let's say this is generated by A, and let's say this is generated by B. Okay, so in fact, this is a free group generated by two elements with one generated for each Z. So why is this like this? So we know that this Z is a free group generated by one element A, this Z is a free group generated by one element B. Now when we take the free product, okay, so we are not adding any relation. So what we are doing is we are just writing down the elements. So for example, A N1, B M1, up to so on, A NK, B NK, okay, up to so on. So remember, we can't write down two elements from the same group. Okay, so if one element is from this Z, then the other element will be from this Z. So if it is one is the power of A, then the next one should be power of B, and the next one should be power of A. Of course, if there are two consecutive powers of A, then we can add the powers, and it will be another element of this Z, and we replace that consecutive powers of A with their product in this Z. Okay, so similarly, if there is identity element inside this word, then we just delete the identity. So in other words, we can say that if there is an element A square B raised to power 3, then the inverse of this element, okay, so has inverse b raised to power minus 3 a square. Okay, so why this is the inverse? Because guided by these two rules, we can easily see that this is the inverse. So why? Okay, so we know that a square b cube. So if it is the inverse, then when I will multiply this with this element, then I should get the identity element. So let's multiply it from this side, then b raised to power 3, b raised to power minus 3. So two consecutive elements from the same group. If there are two consecutive elements, take their product in that group. So b raised to power 3 into b raised to power minus 3 is b raised to power 0, but b raised to power 0 is identity. So if there is identity, delete the identity. So it is basically equal to a square identity of b. Okay, so this b subscript means the identity of this z generated by b, and a raised to power minus 2. If there is identity, just delete the identity and we will get a square a raised to power minus 2. So repeating the same discussion, this is equal to identity. And similarly, we can see that when we will multiply this element from the other side, we will get the identity. Okay, so that's what free product means. So free product of z with itself is basically a set of all words in a and b, and no consecutive elements from the same group, and no identity, no appearance of identity, because if there is identity, then just delete the identity. Okay, so this was an example of free product of two free groups. So consider an example where we are taking the free product of two groups, because we didn't impose any condition on G alpha that they have to be free groups. So they could be groups with relations as well. Okay, so if I have this Z2, so I can take one of the Z2 to be generated by a, and of course this a square is equal to 1. So there is one relation in the presentation of this z. This is not a free group. Okay, so there is one relation, a square equal to 1, and of course this implies that the elements of z2 are 1a. And similarly, take another z generated by b, and of course if it is z2, then there will be only two elements. So there is this relation, b square is equal to 1, and the elements of this z2 are 1b. Now here the generator of z2 does not commute with each other, but they are relations in this free product. Okay, so if we take the free product of z2 with itself, okay, so this z2 is generated by b, this z2 is generated by a. So okay, so now we can say that when we are taking the free product, we are not imposing any condition on the generators of different copies or different groups inside that free product. So there is no relation involving a and b, but there is a relation involving only a, which is a square equal to 1. There is a relation involving only b, which is b square equal to 1, but there is no relation involving a and b in this free product. Okay, so that's what it means. So basically free product means we are not adding any further relations than the groups already have. Okay, so in this example of z2, free product z2, the relations of a and b remains the same, but there are no extra relations. So in other words, we can say that this is equal to ab such that a square is equal to b square is equal to 1. No further relations between a and b. Our next section is Van Kampen's theorem. So what is Van Kampen's theorem? So we know what is a fundamental group of a space. Now if I have a space which is basically collection of path connected components, then we know that this path connected component has its own fundamental group. So as a matter of fact, if there is a path between any 2 points, then the group of homotopy classes of loops at this point, denoted by pi 1 of x, x naught, is basically isomorphic to the group of homotopy classes of loops at this point, which is so this group of homotopy classes of loop at y naught is denoted by this. So if there is a path between 2 points, then the homotopy classes of loops at that point and the homotopy classes of loops at the other point, they are isomorphic to each other. So we can say that if it is a path connected component, then the fundamental group at each and every point is the same. So we can say that one path connected component has one fundamental group. So let's denote it by x naught. And similarly, if I have another path connected component, so let's say there is an element m naught, then there will be fundamental group of this path connected component pi 1 of x m naught. Similarly, if there is another element in another path connected component, then it has its own fundamental group. Now the question is, what is the relation between the fundamental groups of these path connected components and the fundamental group of this space X? So the answer to this question is given by Van Kampen's theorem. So what is the rough idea? So the rough idea is, so for example, in this case we have 3 path connected components. So take the free product of these 3 groups. Okay, so pi 1 of x m naught and free product with pi 1 of x n naught. Okay, so and there is a map. Okay, so there is a map which takes from the free product of these 3 groups to the fundamental group of x. Now what are the properties of this map? So this is a question mark, and the answer to this question mark is given by Van Kampen's theorem. So let's see what is Van Kampen's theorem. So if we have X, which is a topological space which is union of path connected open sets A alpha. Now remember, we are not imposing any condition on these A alphas that they must be disjoint or not. So for example, in this discussion we took these path connected components as disjoint, but they may not be disjoint. So for example, consider this picture. In this picture, if this is A1, this is A2, this is A3, this is A4, this is A5, then we can see that they are not disjoint with each other, of course. So A1 and A5 they intersect at these 3 points, these 3 sets, and A1 intersect with A4 up to so on. Okay, so but we have these AIs, and the only condition is that they must be path connected. So A1 is path connected, A3, A2, A4, they are path connected, but we can see that the intersection of A1 with A5 is not path connected. Okay, so that's important thing to note. Okay, and containing a base point x naught belongs to x, and if the each intersection A alpha intersection A beta is path connected, then the homomorphism is surjective. Now we are getting one condition on this map. Okay, so if we have open sets A alpha, and of course if they are path connected, then they will have their own fundamental group, and if the intersection is path connected. Now in this picture we can see that the intersection of A1 with A5 is not path connected. Okay, so this part is not connected to this, is not connected to this. So in this case we can say that the map pi 1 of A1 with some base point. Okay, so I'm ignoring the base points. Okay, so star pi 1 A2 star pi 1 A3 up to so on, star pi 1 A5 to pi 1 x, not surjective. Okay, so not surjective. Okay, so in this case it is not surjective, but if the intersection is always path connected, then this map is surjective. Okay, so if in addition each intersection, okay, so if we take the intersection of any 3 components, and if this is path connected, then the kernel of phi is the normal subgroup n generated by all elements of the form. So what are these elements? Okay, so basically if I have I alpha beta to be a map from pi 1 of a alpha intersection a beta to pi 1 of a alpha, and if I have I beta alpha to be a map from pi 1 a alpha intersection a beta to pi 1 of a beta. Okay, so these are these maps, and the kernel is generated by elements of the form this. So what is this omega? Of course, omega is basically an element of this. Now if omega is an element of pi 1 a alpha intersection a beta, then I can apply I alpha beta on this omega, and this will be an element of pi 1 a alpha, and given omega belongs to a1 intersection a beta, a alpha intersection a beta, then I can apply I beta alpha and I will get an element of pi 1 a beta. Now I can take the inverse of this as well. Now this is basically an element of the free product of pi 1 a alpha. Okay, so this should be pi 1 over here. So this is one element. Okay, so this is going to give me one relation, and the elements of this form, all the elements of this form will give me a relation, and we will get the following isomorphism. Okay, so the kernel of this phi. Okay, so let's go again and see. So the kernel of this phi is normal subgroup n generated by all elements of the form this. So each and every element of this form, and there is this following isomorphism. So this is basically the free product of the fundamental groups of a alpha, and we are taking quotient with n, where n is the group generated by all these elements of the form this, and there is an isomorphism. Okay, so we have this important relation between the fundamental group of this topological space X and the fundamental group of a covering. We can say that these open sets A alpha cover the whole space, and these A alphas are basically they are path connected. So if they are path connected, we can calculate the fundamental group, and there is this following map. This map is surjective if the intersection of any two open sets is path connected, and of course otherwise it will not be surjective. And if in addition the intersection of any three path connected open sets A alpha is basically path connected, then we can write down this isomorphism, which will give me that the fundamental group of the space X is isomorphic to the free product of the fundamental groups of A alphas quotient with the n generated. So this n is generated by all the symbols of the form this. Okay, so that's Van Kampen's theorem, and which is very useful result. Okay, so to see further some non-trivial examples of this result, we will have to look at another definition of wedge sum. So what is wedge sum? So if we have a collection of spaces X alpha with base points, so in other words we just picked up some points from each and every X alpha, and we are calling that as base point. Because to calculate the wedge sum, we are going to need those points. So the wedge sum of X alpha denoted by this symbol is the quotient space of the disjoint union in which all base points are identified to a single point. Okay, so for example, if I have two circles, okay, so with the base point x0 and let's say base point x1, so there are two circles S1, so two topological spaces with two base points. Now take the disjoint union of these two circles. Okay, so let's call this S1 to be alpha 1 and this S1 to be alpha 2. So alpha I is basically equal to 1 to 2. So this is the disjoint union of these two circles. Now what is the wedge sum of these two circles? So if we identify these 2 points, okay, so in the quotient space these 2 points becomes the same. So in other words, we can say that the wedge sum of these 2 circles is going to be something like this. So we identified these 2 points, okay, so if we identify these 2 points, then we get a shape like this. Okay, so basically disjoint union of SI quotient with the fact that we are identifying the base point. So now let's see how we can use Van Kampen's theorem to calculate the fundamental group of the wedge sum of these 2 circles. Okay, so basically it's a space like this, and we can take this part to be A1 and this part to be A2. Okay, so basically they intersect at one point, and one point is path connected. So basically we can say that pi 1 A1 free product pi 1 A2 going to pi 1 S1 wedge S1 is surjective, because the intersection is path connected. Now there are only 2 sets, and so there is no triple intersection, so that's why this condition is satisfied. And so we can say that we have the fundamental group of this wedge sum to be equal to Z star Z. Okay, so we can easily see that this relation is empty in this case, okay, because we are coming, so whenever so the intersection A1 intersection A2 is this point. Okay, so whenever we apply I alpha beta, okay, so from the intersection, then this is just a point, and the point has trivial fundamental group, so this is just going to be identity. Okay, so when we apply I on the identity, we will get identity, and when we will get I beta alpha on identity, we get identity. So that's why this is trivial in this case. So we have the free product of Z with itself as the fundamental group of S1 wedge S1. Okay, so so there's a little remark that Van Kampen theorem is really useful. So as we have seen in the example of S1 wedge S1, if there are just 2 sets A alpha and A beta in the cover of X, so that there is no condition of the triple intersection, since there are only 2 sets, and in this case we get the following thing. And in the case of wedge sum, we saw that this n is trivial, but in general this n may not be trivial, but if we have only 2 sets, then it's very easy to calculate this n. So now start with the next section of today's lecture. It's the comparison of the homology and the fundamental group. Now homology is basically very useful, and when we converted when we started doing homology, then in the in that motivation I told you that we are basically doing homology as an alternate to the higher homotopic groups. Okay, so so why we want to do higher homotopic groups? Because we know that pi 1 is only useful for lower dimensional spaces like surfaces, and if we go to higher dimensional spaces, for example, if we consider the fundamental group of n spheres, then they are the same for each and every n. Okay, so that's why this pi 1 is not good for higher dimensional spaces. So that's why this pi n is really useful. But then the point is, these pi n's are really complicated to calculate. So then we opted for a little relaxed version of these higher homotopic groups, and then we started studying the homology. And now we are going to compare H1 and pi 1, and basically we will realize that pi 1 contains much more information than H1. But once again, the point is homology groups are relatively easy to calculate, so that's why we calculate homology rather than these higher homotopic groups. So let's start with our comparison of H1 and pi 1. So we know that the fundamental group of the following diagram, which is S1 wedge S1 is Z star Z, so the free product of Z with itself. Now in this diagram we can easily see that, so if I take this to be alpha, okay, so let's say the generator of this Z is alpha and the generator of this Z is beta, then since it's a free product, so that's why A star B is not equal to B star alpha. Okay, so this is just coming from the definition of the free product. Okay, so in other words, we can say that these two words are not homotopic. Okay, because if they are homotopic, then the fundamental group is basically the group of homotopic classes of loops. Okay, so if these alpha star beta and beta star alpha are homotopic, then they would be the same element in this fundamental group, but they are different, so they are not homotopic. So that's one observation. Now we can also observe that in this space, okay, so we can calculate the homology of this topological space as well. So to calculate the homology, we will have to come up with the maps from simplicial complexes to S1 wedge S1. Okay, so we can calculate, so in particular we can take a singular one simplex, so which is a map from standard one simplex to S1 wedge S1. Okay, so so basically I can for example I can take this element, so starting from this point, going like this and going like this and then coming back like this. Okay, so starting from this point, so basically taking alpha and then taking beta. So first apply alpha and then apply beta. Okay, so I can define this sigma to be a map from this standard one simplex to this wedge, such that this sigma is equal to, so first moving around alpha and then moving around beta. And then I can also define another sigma prime from the standard one simplex to the wedge sum S1 wedge S1, such that I start from basically this beta and move on and then move along alpha. Okay, so going like this, this, and so sorry, going like this, it should be like this. Okay, so basically it's basically, so first moving around beta and then moving around alpha. And we can also see that these two elements are the same in the homology of S1 wedge S1. So in other words, we can say that they are homologous. Okay, so the elements A star B and B star A are not homotopic, but they are homologous. So that's one observation. Okay, so that says that two elements which are same in this set and these two elements are not same in this set. Okay, so that's our motivation for our further discussion. So let's go on and start precisely the relation between the H1 and pi1. So the first observation is if we have one simplex, okay, so for example if this space and if we have this one simplex, which is basically a continuous map from the standard one simplex to X, we can define this map D from the standard one simplex to I, okay, such that, so D is given like this. Now remember that this standard one simplex is basically given like this, E0 E1, and also we know that we can take the points of this standard one simplex to be of the form 1 minus T E0 plus T E1. Okay, so these are the elements of the standard one simplex. So if you remember, then basically this is the line segment from E0 to E1, because this is the standard one simplex, so it is generated by two basis elements of R2. So this E0 is 1 0, this E1 is 0 1, and this line segment is basically the standard one simplex. Now we can define this map D from the standard one simplex to I in the following way. So just take this value t, this parameter t, and d of this element is equal to the parameter t, because geometrically we can say that each and every element on this line segment has some value of parameter. So basically we are taking that value of parameter from that point and mapping into that I. Okay, so of course in this case t varies from 0 to 1, and so for each and every point we have some value of t, and so we get this map. Okay, and using this d from this standard one simplex to I, we can define the following map. Okay, so how we can define this map? So let's see. So remember that what is this group? So this is the group of all homotopy classes of loops. So what is a loop? A loop is basically a continuous function from I to x such that f of 0 is equal to f of 1. Okay, so f of 0 is equal to f of 1, and this f of 0 is the base point. Okay, now we know that I can define a function from this standard one simplex to this I. Okay, so this function d is basically a continuous function. Okay, so I have this function d. So I have this element f, which is an element of this pi1 of x x0. Then I can define using this f the following function, which is the composition. Okay, so f d, or f composition d. So I can define this function, which is a continuous, because d and f are continuous, so that's why this composition is continuous. And so I have a continuous function from this standard one simplex to x. In other words, I have a singular one simplex. So if I have a singular one simplex, then of course it's an element of h1 of x. So that's how we take any element of this pi1 of x, and we get an element of this h1 of x. Okay, but of course we have to see that if this map is well defined or not. So for that we have our next result, that this map is well defined. Okay, so what do we need to see? So we need to see that if f and g are the same elements, so then their image are the same. Okay, so that's what we have to show. So pi1 of f is equal to phi of g. Okay, so phi of f is equal to phi of g. So that's what we have to show. So this is to show. Okay, now let's see how to proceed this discussion. Now we know that given any loop inside x, so let's call it f, then I can define an element of h1 of x. So using this diagram, that there is this map D from standard one simplex to I, and then we can define this map F composition D. Okay, now also we know that if I have a map, a loop inside X, okay, so if I have a loop inside X, which is basically a map from I to X, then I can split this map through a circle. Okay, so through this map U and this map F prime. So what is this map U? So given F belongs to pi1 of x x0, there exist U and F prime such that diagram 2 commutes. So what is diagram 2? So this is diagram 2. Okay, so what is this map U? Such that this U of t is equal to e raised to power 2 pi I t. Okay, but if you're not convinced, then this is a little exercise for you, that this really happens. Okay, so or you can have a look at the book of Joseph Rotman, okay, and or you can have a look to Google. Okay, so we have this map u of t, and this map f prime is basically a continuous function from s1 to x. Okay, so if we have a continuous function from s1 to x, then f prime from s1 to x, which is continuous, implies a map between the homologies of s1 and x. Okay, so this is a very simple observation, and we have seen this thing many times in our previous discussions. Now start from this element f composition d, and we know that if f is basically a loop inside x, or in other words the class of f is an element of this fundamental group, then fd is basically an element of h1 of x. Okay, now I can write it down in the following way. So basically there is this map D, which is basically from the standard 1 simplex to I. So this D to F can also be written as this D, U and F prime. So basically this is equal to, so first apply D, then apply U, and then apply F prime. Now if you look at this UD, so basically start from this standard 1 simplex, apply D, and then apply U. Then basically this is an element of H1 of S1. Okay, so this belongs to S1 of S1. Okay, so singular 1 simplices, so the free abelian group generated by the singular 1 simplices of this circle S1. Okay, and how we take the image of this, so basically this is equal to f lower star of prime and the class of UD. Okay, so that's our first observation. Now of course when we apply this f prime on this, then this is just equal to taking this image under f star prime of this element of h1 of s1. Okay, so once again this ud, so start from this d and this goes to u. It's a continuous function from standard 1 simplex to x1, hence an element of this free abelian group generated by singular 1 simplices of s1. Okay, so how we take this image, so as I said, we have seen this function many times. So basically we are taking the singular 1 simplices of s1 and taking the composition with f prime, and then we are getting the element of this. So in other words, this is equal to this. Okay, now if there is another element, okay, so g from I to x, so basically now we are going to this part of the proof. When the classes of f and g are equal, then their images are equal. Okay, so let's consider another element g. Okay, so from I to x, then of course this implies that there exists g prime from s1 to x. Also, if f is homotopic to g, of course this is a relative homotopy, okay, with respect to this I dot, then this implies that f prime is homotopic to g prime. Okay, so that's one observation. Now f prime is a map from s to s1 to x, g prime is a map from s1 to x, and so we can say that if they are homotopic, then f prime lower star is equal to g prime lower star. Okay, so now we are using the properties of the homology. Okay, so using this property, starting from equation number 1 again, we can write it down as f lower star ud is equal to g lower star prime, because these two are equal, ud, and this is equal to g prime ud, and which is equal to, okay, so this is g, so first applying d and then applying u and then applying g prime is the same as first applying d and then apply g. So basically first apply d and then apply g. Okay, so from equation 1 we basically started from f composition d or fd. Okay, so it is the same. Okay, so this expression says that the homology class of f and g are the same, because this is basically phi of the homology, so homotopy class of f, and this is basically phi of the homotopy class of g, and they are equal. If f and g are equal, okay, so then these two are equal, and where we use this fact that f and g are equal, so here we use this fact that if they are homotopic, okay, so the classes are equal, then they are homotopic, then f prime and g prime are homotopic, and so they will generate the same space, and then we get this following thing. Okay, so once again, if you are not convinced, then I can leave this as an exercise. This is also available in Joseph Rotman's book. So that's the end of the proof, and so this map is well defined. The function phi, which is a function from the fundamental group of x to h1 defined above, is called the Horowitz map. So this Horowitz map is a homomorphism. So how to prove that this map is a homomorphism? So the proof is basically very simple. If we have two functions, okay, so f and g, so in here, and we know that we can multiply two elements from here, and the image is basically, so f into g is basically equal to f star g, and we are talking about in pi 1 of x naught. Okay, so that's how we define the multiplication. Now what do we need to show? That if we want to show this pi is homomorphism, so we want to show that the product, okay, so this is equal to phi of f and phi of g. Okay, so the homotopy class of g. So that's what we want to show. Okay, so to prove this, consider this 2 simplex, okay, so generated by E0, E1 and E2. Okay, so in this 2 simplex, we know that it is basically, the boundary of this is these 3 1 simplices. Okay, now sigma, let's call it sigma, is a 2 simplex from the standard 2 simplex to the space x. Okay, now we can define sigma of 1 minus t 0 to be equal to f of t. Okay, so basically it is this line. Okay, so in this case you can see that there is no contribution of E2, so it is this line segment from E0 to E1, and we are defining it to be f of t. Okay, so we are defining this sigma like this. Okay, so and so on this line there is E0, there is no E0, so this 1 minus t we are defining to be g of t. And similarly we can define sigma on this portion, so there is no contribution of E1, so basically 1 minus t 0 t to be equal to f star g. Now we can define sigma on the line segment. So first divide this line segment joining E0 and E1 into 2 parts, and then define the sigma on this line segment in the following way. Okay, so the line segment which will join this part with this line as constant. Okay, so in other words, if the initial point of the line segment is basically 2 minus t divided by 2, so there is no contribution of E1, 0, and t by 2. Okay, so basically it's this line segment, 2 minus t divided by 2, 0, t by 2. So we can see that when t is 0, then basically it is 1, 0, 0, so E naught, and when t is equal to 1, then basically it is equal to 1 by 2, 0, 1 by 2. So basically it is this point, the midpoint of E naught and E2, and so if the first point is from this line and the second point is from this line, so of course we know what is this line. This is equal to 1 minus t, t 0, then this is constant. Okay, so sigma, okay, so let's call it b, so 1 minus t, t 0, so sigma is constant on the line joining A and B for each t, for each value of t. Similarly, we can define this number c. So c is any point on this half line segment. So of course the general point of this is 1 minus t divided by 2, so there is no contribution of E, so 1 plus t divided by 2. So let's see if it is a required line segment. So when t is equal to 0, it is 1 by 2, 1 by 2, so this point. When t is equal to 1, then there is no contribution from this side, and there is only contribution of E2, so that's what our E2 is. And similarly we can define this d to be, so 0, 1 minus t, t, so basically it is this portion. Okay, so 0, 1 minus t, t. So sigma is constant on the line segment joining C and D for all t. Okay, so now we have constructed our sigma because we have given the value of sigma for each and every element of this 2 simplex. Now we can calculate the boundary of sigma. So basically this is equal to the image of sigma of this side, so basically the one simplex generated by this. So so first we will delete E naught, so basically E1, E2, okay, minus, then we will delete E1, so we will get E naught, E2, and then we will delete E2, so basically plus with E naught, E1. Okay, so that's the boundary, but now we know that sigma of E1, E2 is basically G of t. Okay, okay, because E naught, E1, that's what we define, that this is equal to G of t, and E naught, E2 is basically F star G, and E naught, E1 is F of t. So that's the boundary of this sigma. Okay, so now start from this image, so start from this side, so phi of the class of F multiplied by the class of G. Okay, so this is basically equal to phi of the class of F star G, and which is basically equal to the class of F star G composition with D. Now D is basically map that we already defined from the standard one simplex to I. Okay, so that's the image, and of course this image is inside H1 of X. Okay, now we have proved that F star G and F plus G, so they differ by an element of the boundary. Okay, so if two elements differ by an element of the boundary, so in this definition of H1 of Z, so this is equal to the cycles quotient the boundary, so the elements which are boundaries of some elements of S2 of X. Okay, so F star G and F plus G, they differ by an element of the boundary, so in other words we can say that they are the same, so we can write it down as F plus G composition with D. So basically we can say that this is equal to F composition D plus G composition D. So what is F composition D? So basically this is equal to phi of F and plus phi of the homology class of, sorry, the homotopy class of G. Okay, so that's what we have proved. So basically this phi Horowitz map is basically a homomorphism. So this Horowitz map is natural in the following sense: if we have a continuous function from x naught to y naught, then we have the following Horowitz map from pi 1 of x naught to h1 of x, and pi 1 of y naught to h1 of y. And of course if there is a continuous function from x to y, then there is another map which is h lower star between the homologies. Okay, so if there is a continuous function, this h is the continuous function from x naught to y naught. Okay, so this h lower star is the corresponding map between the homologies, and this h lower star is the map between their fundamental groups. And for each and every fundamental group, pi 1 of x naught and pi 1 of y naught, there is this Horowitz map, and this diagram commute. So that's one important property of the Horowitz map. Now let's recall one other definition from our previous discussion. Given a group, we can define its commutator subgroup. So it is basically the group generated by all symbols of the form this A, B, A inverse, B inverse. So the group generated by all elements of this form is basically a commutator subgroup, and we are going to use this on our further discussion. So that's Horowitz theorem. So in Horowitz theorem we use this commutator subgroup, and this Horowitz theorem is basically gives us a precise picture of the relation between h1 and pi 1. So what's the relationship? So if x is path connected, then the Horowitz map is surjection with kernel, the commutator of this fundamental group. Okay, so let's go back and see the commutator group. So this is denoted by this bracket G comma G. So this is the commutator subgroup of this fundamental group, and we are taking quotient of the fundamental group with this commutator, and then we are getting this h1 of x. And of course there are many consequences of this theorem. So for example, if pi 1 of x naught, okay, so if this is abelian, so if this is abelian group, then in an abelian group, A, B, A inverse, B inverse, so this is just equal to A inverse, B inverse, because it is commutative, so I can commute these two elements. So basically this is equal to identity. So this commutator subgroup is trivial, and that's why if pi 1 x is abelian, then this implies the first homology group and the fundamental group pi 1 of x naught, they are equal. So that's one consequence. But in general, if pi 1 is not abelian, then there is this relationship. So in other words, we can say that we are taking quotient with some subgroup. In other words, we are hiding some information. Okay, we are taking quotient, we are taking some elements of this pi 1 of x naught to be 0. Okay, so when we are taking quotient, we are making some elements of this pi 1 to be 0. In other words, we are hiding some information, and then after hiding this information, we are getting this h1. So in other words, pi 1 of x naught contains much more information than h1x. Okay, so as a little corollary, we can say that h1 of s1 is isomorphic to z, because we know that the fundamental group of S1 is basically Z, and this Z is basically abelian. So as I said earlier, that in case the fundamental group is abelian, then this is exactly equal to the first homology of the space. And similarly, another important consequence is if X is simply connected, in other words, all the pi 1 x naught are trivial. Okay, so in other words, this is path connected and all the fundamental groups are trivial. So in this trivial case we can say that this commutator subgroup once again is trivial. Okay, and then we can say that h1 of x is also 0. So this relation between h1 and pi1 gives us another important tool for calculation of the homologies. Okay, so if we want to calculate homology, then we have to understand all these tools. Now in general, if I want to calculate h1 of sphere, then this is 0 by our previous result, and we also know that if I want to calculate the h1 of a torus, then this is equal to this free abelian group z plus z. In general, if I want to calculate h1 of a surface of genus M, okay, so if there are M holes, okay, so M holes in it, then basically it is equal to the free, so direct sum of these z's, and how many copies? So basically 2m copies. So in general, so we are not doing the proof of this, but if you are interested, you can have a look at the book of Joseph Rotman. So last but not least, we have this relation between the simplicial and singular homology. So there are many ways of calculating the homology, and we have done two ways. So one of them is simplicial and the other one is singular homology. So each and every technique comes with its restriction of the domain. So for example, we can calculate the simplicial homology only for simplicial complexes, and we can calculate the singular homology if we can handle the structure of the free abelian group generated by the singular n simplices. Okay, so but if we want to calculate homology using both methods on a space for which we can calculate both homologies, then what will be the result? Okay, so of course we should get the same homology. Okay, so that's what this theorem says. Okay, so if we have oriented finite simplicial complex K, then we have the following thing. Okay, so the reduced homology generated by, so we calculate this homology is using the simplicial homology, and we calculate this homology using the singular homology. Okay, and they are isomorphic. Okay, so this underlying space of this simplicial complex is a topological space, and we can calculate the singular homology of this topological space. And as a corollary, we have the following thing. If we have a polyhedron having the triangulations, okay, k h and k prime h prime, then the homology of these two spaces are equal. So that's another important aspect of the simplicial homology. So when we constructed the simplicial homology, then we haven't so basically we ignored the fact that if we have two different triangulations of the same space, then what will happen with the homology? So this result, so this corollary, which is the result corollary of this important theorem, says that if I have two different triangulations of the same space, then the homologies are basically same. Okay. So next time we will start with another method of calculating the homology called the cellular homology. This is the end of the lecture. Thank you very much, and Allah Hafiz.